Welcome to The Explainer. Today, we're going to talk about something you probably don't think about much, but it's literally what keeps you alive. Your body's own internal ocean. It's this massive, complex system of water that keeps absolutely everything running. So, let's dive in.
So let me ask you something. When you look in the mirror, how much of what you're seeing is actually solid stuff? Your bones, your muscles, your organs. And how much of it is something else entirely?
Okay, let's get more specific. What percentage of your own body weight do you think is just water? Go ahead, take a guess. I bet the real answer is a lot higher than you think.
For an average adult, it's a staggering 60%. Yeah, 60. So that means the majority of you isn't really solid at all. You're basically a walking, talking, carefully balanced aquatic environment. To put that into perspective, let's take a 70 kilogram, that's about a 154-pound adult male. For him, that 60% works out to 42 liters of water. That's more than 11 gallons. All of that is making up about 2/3 of his total body weight. But here's where it gets really interesting. That 60% figure, it's just an average. The actual amount of water in any given person's body can change quite a bit, and it all depends on a few key factors. For starters, age and sex play a huge role. Take a baby, for instance. They're about 75% water, which is why they can get dehydrated so easily. On the other hand, an average adult female is usually closer to 50% water. And this table points to the other big factor: body composition. It's actually pretty simple. Lean muscle tissue holds a ton of water, about 73%. But fatty tissue, it holds very little, only around 20%. So that's why, as you can see, a person's body fat percentage has a direct impact on their total water content.
Okay, so we've established that we're all carrying around a lot of water. But where is it all? I mean, it's not just sloshing around in one big pool inside of us, right? Nope. It's organized into these incredibly precise compartments. Let's take a look at the map. So at the highest level, it's a pretty simple 2/3, 1/3 split. The vast majority of all that water in your body, about 66% of it, is actually locked away inside your trillions and trillions of cells. So let's break this down with our 70-kilo guy and his 42 liters of water. A full 28 of those liters are found inside his cells. We call that the intracellular fluid, or ICF for short. The other 14 liters are on the outside of the cells, and that's the extracellular fluid, or ECF.
Now, that extracellular fluid is a really big deal. It's the internal sea that bathes all of our cells, delivering nutrients and carrying away waste. So let's zoom in a little closer on that smaller 14-liter compartment.
So this ECF is itself split into two main zones. First, you've got plasma. That's the liquid part of our blood, inside the blood vessels. And second, there's the interstitial fluid, which is the fluid that's literally bathing every single cell in your body. And they are almost identical except for one absolutely critical difference: protein.
See, plasma is packed with proteins, but the interstitial fluid has hardly any. And this difference in protein creates this amazing pulling force, almost like a magnet for water. It's called oncotic pressure, and it is the absolute key to moving fluid exactly where it needs to go.
And that brings us to the most dynamic, most active part of this whole story: the constant exchange of fluid between these compartments. It's like this beautiful, microscopic ballet of pushing and pulling that's happening all the time. So think about it. How does the water carrying all that oxygen and all those nutrients actually get from the plasma inside your tiny little capillaries out into the interstitial fluid and finally to your cells? Well, the answer lies in something called Starling forces. The easiest way to think about it is like a constant tug of war. On one side, you've got a pushing pressure from the blood. That's called hydrostatic pressure. And on the other side, you've got that pulling pressure we just talked about, the oncotic pressure, which is created by all those proteins in the blood. So here's how it works. At the beginning of a capillary, right where the blood enters, the push from blood pressure is really strong. It's so strong it literally forces fluid out of the capillary to deliver all the good stuff. We call that filtration. But as the blood moves along, that push pressure drops. Now the pull from the proteins is stronger, and it starts drawing fluid and waste products back in. That's called reabsorption. It's this perfect little system of delivery and pickup. So what's the big takeaway here? It's that this entire incredible system is designed to maintain a perfect, delicate balance, or what scientists call homeostasis. And when that balance gets thrown off, trust me, we feel it almost immediately. I'm sure you have. We all have, right?
That thirst, maybe a headache, feeling a little sluggish. But what is actually happening on a cellular level when you're dehydrated? Well, when you don't drink enough water, the fluid outside your cells, that extracellular fluid, it becomes more concentrated or saltier. We call this a hypertonic state. And water has one simple rule. It always moves toward the more concentrated area. So water gets pulled out of your cells, causing them to literally shrink and stop working properly.
Now, this leads to a pretty common question. If being dehydrated is so bad, does that mean more water is always better? And the answer, which might surprise you, is a definite no.
Yep, if you drink way too much water, way too fast, you can actually create the exact opposite problem. The fluid outside your cells becomes too diluted, what we call a hypotonic state. And now, water rushes into your cells to try and balance things out, causing them to swell up like balloons. And as you can imagine, this is especially dangerous for your brain cells.
You see, our bodies are absolute masters of balance. As this table shows, to stay healthy, our daily water intake has to perfectly match our output. What we bring in from food, drinks, even our own metabolism has to equal what we lose through urine, sweat, even just breathing. That perfect balance? That's homeostasis.
And this all brings us to this really profound thought from Claude Bernard, the 19th century physiologist who first figured all this out. He said, "The stability of the internal environment is the condition for the free and independent life." Just think about that. Every sip of water you take, every breath, it's all part of maintaining that delicate, life-giving stability inside of you. It's not just water, it's the ocean within.